Hi, I'm Thomas. Today I'm going to be talking to you about the 100 prisoners problem. In this problem, we have 100 prisoners on death row, and they're trying to escape. Each of them has 50 guesses to guess their number inside of an array of 100 suitcases. Each suitcase has a hidden number, 1 through 100, and a shown number, 1 through 100. And each of the prisoners has an assigned number. We're going to call the top number the hidden number, and the bottom number the shown number. Okay, and then we're going to randomize the numbers inside. Okay, so this problem seems really hard, right? 50 guesses for each prisoner. So the first one is going to have a 1/2 chance to guess their number. That suitcase is going to be eliminated. And so the next person is going to have a slightly higher chance. But for all 50 prisoners to escape, they all have to get the right number. And so that seems like a vanishingly small probability for all of them to get it right. But there is a correct strategy. And the correct strategy involves graphs. So what we're going to do is we're going to connect up this graph, treating each of the suitcases as a node. And the way we're going to do this is connect each hidden number to the corresponding shown number. And so I haven't drawn all the suitcases, so I'm not able to do this for all of them, but I did choose my numbers a bit deliberately, so we're able to do this a little bit, as you'll see. Right, and this is a well-defined process because there are 100 shown numbers, 100 hidden numbers, 1 through 100, and so you know that every single integer, 1 through 100, is going to show up twice. Once as a shown number, once as a hidden number, and so you can connect up all the suitcases. In this example, we have a 3 loop, a loop of 3 suitcases. If it was prisoner's number 10's turn, they can use this graph to do the optimal strategy. So they would start at the suitcase with their shown number, and remember they want to get 10 as the hidden number. So they look inside suitcase number 10, they see a 3. So they go to suitcase number 3, they look inside, they see an 11. They go to suitcase number 11, and they find a 10. Wow, they did it, right? When I do it like this, it doesn't seem so surprising, but yeah, this is a pretty nifty little strategy. And we can reduce the problem of how likely is it that all prisoners escape down to at least the probability that no loop greater than 50 appears, right? Because if there was a loop that was longer than 50, and each prisoner has only 50 guesses, then they could start on the right loop where their number is somewhere in some suitcase on the loop, but they might not make it to their number because they'd run out of guesses. Okay, now we're going to look at the combinatorics of this problem. So how we're going to do this is we're going to translate our previous view of the problem with all the suitcases laid out in a square array, and we're going to turn it into something a bit more useful. So what each graph is defined by is just the suitcases. And each suitcase is no more than a pair of numbers, right? So okay. So in this case, this would be a 1 loop, by the way, because this would be 1 suitcase, and a prisoner whose number was 100 would look inside and find their number. Wonderful. They're a lucky person. So we can draw these loops and connect up the graph like this. All right, if there's a 2 here, then that gets connected, etc., etc. The important point is that each graph is defined by nothing other than this. Okay, then we can count how many possible graphs we could have. Well, that is just the number of ways that we can rearrange this right-hand column. And so we could put the 5 in anywhere from 1 to 100 spots. Once we've placed the 5 somewhere, we could put the 7 in anywhere from 1 to 99 spots. And so you might see what's happening. This is just a factorial. Now, if we want to get the probability of there being a loop of length 51 or greater, then we want the number of possible graphs that have a loop of length 51 or greater. And then we're just going to divide that by 100 factorial. So how we're going to do this is we're going to break it up into parts. So we're going to start with the number of possible ways to choose 51, or let's say just some number r of nodes to form a loop of length 51 or greater. Then, that doesn't fully define the graph, right? We just picked the nodes. Well, we also have to account for the number of possible ways that these R nodes can be rearranged in the loop. So this is saying, okay, I could have the suitcases be 3 and 41, or I could have 41 assigned to some other number in the loop, 8 or whatever. We can think of this as the number of ways to rearrange links in the loop. And then the rest of the graph is defined by all the other nodes that weren't included in the loop. And again, we can rearrange them in any order, and that defines this column entirely. And so that's going to be okay. And then the number, so if we multiply all 3 of these numbers together, we should get the number of possible graphs that have loops of length 51 or greater. And then we divide that by 100 factorial to get the probability of there being a loop of length 51 or greater. And we're going to add up for all values of r greater than 50. And things cancel really nicely here, it turns out. What we get is this is equal to and this is going to be equal to, you see the 100 factorial cancels in each term, and in each term the 100 minus r factorial also cancels, and then r minus 1 factorial over r factorial is nothing other than r, and so this is just going to be again, this is the probability of there being a loop greater than 51. So the probability of there not being a loop greater than 51, in other words, all of the prisoners escaping, is okay, so 31% chance of surviving. Still not great, wouldn't want to be in their situation, but that's better than what it would have been with random guessing, right? A lot better. So just quickly, how do we make sense of this? How we make sense of this is that there is not just one piece of information in each suitcase, right? It's not like the prisoners are reaching into some bag and pulling out a suitcase or something, right? They're not randomly choosing a suitcase. These suitcases are numbered with certain numbers that are shown. And so we're taking advantage of that extra information. you could also think, okay, maybe we don't even need to number the suitcases. As long as they are arranged in a consistent array in the room and each prisoner knows how to associate the position in the room with the number, then we're good. You could also have letters showing instead of numbers, right? As long as you have some way of identifying the thing that is shown on the suitcase with what is inside, one-to-one mapping, right, in math terms of bijection, then you're good. And so this is a really fascinating problem. It's sort of like the Monty Hall problem, which I don't have time to go into, but yeah, it's a very non-intuitive sort of system where there is extra information that on first glance you don't really notice. So thanks for listening. Have a good day.